Nuclear Chemistry, Part 5, Half-Life. In this video, we'll be predicting the final amount of a radioactive nucleus that remains after a certain number of half-lives have occurred. If you recall, the rates of chemical reactions tend to depend on several factors like concentration and temperature and the like. Nuclear decay is a spontaneous process, so you cannot change the rate of decay for a nuclear reaction. The decay of a single nucleus is completely random, but in total, radioactive decay is one of the most steady, predictable things we can measure. That predictability leads to a concept called half-life. The half-life of a radioisotope is the time it takes for half of its nuclei to undergo radioactive decay. Half-life is a time, first and foremost. It's not an amount, it's a time. So it has units of time, like seconds or years or weeks. Half-life is a time. It's the time it takes for a sample to go from 100% down to 50%, as shown in the graph. A second half-life would be the time, same time as the first, by the way, it takes to go from 50% to half of that, which is 25%, and so on. The time of half-life is unchanging for a specific decay for a specific radioisotope. You can't change it by changing concentration or pressure or temperature. Because it's so steady and predictable, half-life can be experimentally measured for many different isotopes. As an example, the half-life of radon-222 is 3.8 days. That means that however much radon-222 you had in your sample 3.8 days ago, you've only got half of it now. And in 3.8 days, you'll have half of that, and so on and so on. Predictable half-lives are used to date old stuff like ancient artifacts and prehistoric fossils. Two radioisotopes commonly used for this purpose are carbon-14, which has a half-life of 5,730 years, and uranium-238, which has a half-life of 4.51 billion years. So let's solve a half-life problem together. What mass of a 1.8 gram sample of radon-222 with a half-life of 3.8 days will remain after 19 days? To solve this problem and similar half-life problems, we'll need to employ this two-step process. We'll need to figure out how many half-lives have occurred first, and then we'll divide the original amount, or mass or percentage, of the sample by 2 once for each and every half-life that has occurred. Since radon-222 has been decaying for 19 days in this sample, we'll divide the total time by the time for one half-life. 19 days divided by 3.8 days gives us 5 half-lives. 5 half-lives have occurred for this radioactive decay. Now that we know how many half-lives have occurred, we know how many times we have to divide the original mass by 2. We can show our work by taking 1.8 grams and dividing by the product of 2 times 2 times 2 times 2 times 2, but you'll want to be careful putting that in your calculator correctly. Or we can simply divide the 1.8 grams by 2 5 times, which is the same thing as dividing 1.8 grams by 2 to the 5th power. If we put it in our calculator correctly, we should get something like 0.056 grams. That's what mass of the original 1.8 grams remains after 5 half-lives. Now, how about a second sample problem? What percentage of a sample of carbon-14 with a half-life of 5,730 years remains after 22,920 years? If you're going to need more than 10 seconds, you'll need to pause this one. These are the two steps that we'll need to take to solve this problem, same as before. Did you get stuck on the second step because you didn't know what the original amount was? Well, remember that it would make sense that the original total amount is 100%, because that's what you started with, all of it. So that's what you'll need to divide by 2. How many times? Yes, the total time divided by the half-life shows us that 4 half-lives have occurred. So we'll divide 100% by 2 4 times. That means that 6.25% of the original amount of carbon-14 will remain after nearly 23,000 years have passed. If an original sample of 1 million radium-226 atoms decays for 4,800 years, how many atoms will remain? The half-life of radium-226 is 1,600 years. See you again in 10 seconds. Here's my solution. How'd you do? I determined that 3 half-lives have occurred, so I divided 1 million by 2 3 times, and I got 125,000 atoms remaining. Thanks for watching this video about half-life. There won't be a third one. Confirmed.